But to do this, we need water quality models. So in this presentation, I'm going to show water quality models. So there are two types of water quality models. One, the AI type, the second, hydroenvironmental types. The AI types are quicker, and we can do timely prediction. But if we want more understanding, we have to still use the hydroenvironmental models. And I will show the work in Cardiff University for both models. So here I introduce the Gamma GA ANN model. Basically, the linear model can capture key variables, but it does not capture the possible nonlinear interaction between linear and nonlinear relationships. For the ANN model, we capture nonlinear relationship, but we do not identify key variables. So we introduce a new Gamma GA ANN model for full nonlinear variables, identification, and also water quality prediction. This is the method outline. We first get data, and then we do Gamma GA tests to identify the important variables that governs the process. Then we feed that input into the ANN model, get predictions, and inform the water treatment operators and swimmers. So here is the Gamma test for an input and output plus noise system governed by an unknown nonlinear model. Gamma test is capable of obtaining a noise variance gamma, but unfortunately, without needing to know the underlying model. To use this Gamma test in variable identification, we choose the combination of variables that give the lowest variance, which means the lowest gamma. But to search the entire all combination is very time consuming. Therefore, to save some time, we use the genetic algorithm to solve this minimization problem. We will test this new method in the Swansea Bay, UK. There is quite a lot of beaches along this area, so the water quality in the bay is important for swimmers. Also, it is data rich. We have a lot of measured data in this site for us to validate the model and train the model. So to compare our model, we also conduct other models with different key variable identification and different prediction models. For Gamma GA ANN model and stepwise linear ANN model, we use ANN model for prediction. The other models, we use stepwise linear model for prediction. So you can see the Gamma GA ANN model usually give you the best training results, sometimes also give you the best validation results, but it does not give you the best testing set results for both mean square error and R square, unfortunately. You can also see that the two models that use ANN is better compared to the other model that does not use the ANN. It is because the ANN is good in capturing nonlinear relationship between the inputs and outputs. We can also see how good these models perform as a beach water quality warning models. The European Union separates the beach water quality into poor and not poor according to their enterococci and E. coli concentrations. And I have plotted the performance table accordingly. You can see that our newly devised model, the Gamma GA ANN model, have a higher sensitivity to enterococci compared to the other ANN-related type model. For E. coli, the sensitivity is similar. So we can say that although our Gamma GA ANN model does not give the best R square in all cases, it does improve the sensitivity for enterococci and is better for at least beach water quality warning models. To have a more understanding to the transport and fate of FIO, we conduct the hydroenvironmental model study. It answers the question of where is the source for a measured FIO concentration and what are the contributions of the respective sources to the measured concentration at the measured point. To calibrate our model, we simulate a previous field study on source receptor connectivity. Bacteria are released at 4 different points, and they are measured at 4 different sampling points. In our model, we test 3 ambient conditions. First, the base condition. Second, the wind condition. And the last one with salinity and wind. So here is the results. So the tracer bacteria has released at river Neath. This trace bacteria here is assumed to be conservative, so it is not decaying in this work. When the bacteria reaches one of the data sampling points, the concentration there will increase, signaling the arrival of bacteria. As the bacteria plume moves, the concentration there will be different. Here we compare the measured and modeled bacteria concentration. We first look at bacteria released at river Neath and measured at a sampling location. You can see the model captures the bacteria arrival, and the bacteria arrival time predicted is 3 to 4 hours off. When we add salinity, it slightly improves the arrival time prediction. Here we look at the second test. This another bacteria release point and the other sampling point. We can see that in this case, only with salinity, the bacteria arrival is captured, and the error is also 3 hours, and this shows the importance of salinity. But in our model, the bacteria decay less compared to the measurement. It may be due to that we use a conservative tracers, but in reality, the bacteria may decay. So a bacteria decay model will be employed as our next step. So this is a summary. We have shown the AI and hydroenvironmental models we are studying, which make possible an optimal energy use in wastewater treatment. And we have to do further testing or calibration. Thank you.
Thank you very much. Next, Dr. Christian Appendini from Mexico will present future scenarios on extreme ocean waves in tropical areas. Dr. Appendini is an oceanographer from Universidad Autónoma de Baja California, where he also obtained his master's degree. He's worked in consulting companies in Denmark, Spain, and the US for over 11 years in studies related to coastal and ocean engineering. He's current head of the Coastal Processes and Engineering Lab at the Institute of Engineering, UNAM. Welcome, Doctor, and the floor is yours.
Hi, thanks very much for your presentation. So I'm going to jump into another very different topic. So I'm going to talk about ocean waves in tropical areas and how extreme waves will change in future scenarios. So the last IPCC report of climate change, the physical science basis, which was released a few months ago, it states with high confidence that the proportion of intense tropical cyclones, those are category 4 and 5, and peak wind speeds of the most intense tropical cyclones are projected to increase at the global scale with increasing global warming. So we've been knowing this for a while from the studies of a lot of different colleagues, but this is already stated with high confidence. And there has been a lot of studies related to the effect of tropical cyclones, most of them related towards storm surge, as it has been said here, a lot of population lives near the coast, around 70%. And also a lot about wind damage, but there's very few work related to ocean waves and how ocean waves are going to be changed by the change in tropical cyclones. And this is a very relevant topic in tropical areas, because basically the size of the structures we're going to use for structures in the coastal and offshore areas is related to the size of the waves that are going to be experienced in those structures. So ocean waves are a main design parameter for offshore and coastal structures. And we know that if we cannot do a good determination of the design wave, then we're going to have structure failure. And that is very costly. And in tropical areas, the structure damage in offshore industry is related to ocean waves from tropical cyclones. And I know that we now leaving out the fossil fuels in a changing climate world, but this is also related to renewable energies. So we know in Europe there's a lot of wind farms in the offshore areas. Of course, there's no tropical cyclones there yet. There's a few of them have reached all the way to Scotland as extratropical cyclones. But in tropical areas, we can expect that there's also going to be a change to renewable energies. But still, I mean, we're still extracting fossil fuels in offshore areas. And one of the big disappointments in the COP26 is that they changed the wording from phasing out from fossil fuels to phasing down to fossil fuels. So that means we're going to continue for a while. But in any case, if we move towards renewable energies, and in Mexico, we have the Yucatan platform, which is, I say it's the jewel of the crown, because there's very shallow water and the mean wave climate is really mild. So compared to the wind farms in the North Sea, we have a really nice place to put wind farms in Mexico. Although, of course, we have the challenge of tropical cyclones. So that's a challenge. So the results I'm going to present are focused in the Gulf of Mexico, where we have a lot of different activities going on, and all those are affected in some way or another by the wave climate, and particularly oil and gas and maritime transport is affected by extreme waves. So the design guidelines for offshore structures in the Gulf of Mexico are mainly provided by the American Petroleum Institute, which has provided recommendations for mid-ocean conditions since 1969. But it is since 1976 that it starts giving recommendation about waves. So this is a timeline, which I'm not going to go over it, about the API developments in the Gulf of Mexico. But the first standard, although with no design wave recommendation, came after several tropical cyclones. We had strong hurricanes in the Gulf of Mexico in the in the 60s and late 60s. And since then, in 1976, they recommended the 100 years design wave for design. But then we had some updates on the recommendations after there has been extreme events like the 2005 season and Hurricane Ike. So they have been using historical information to give the recommendation of the 100 years return wave for design. But as we are moving into a changing climate, doing this type of recommendations is not a very good idea, because every time we have a large energetic tropical cyclone season, we have to update the recommendations. But if we already having structures that were just designed for the 2 years before wave climate, they're going to be more exposed to failure. So in 2020, we had the second highest accumulated cyclonic energy season in the Gulf of Mexico. And the question is, are they going to update these recommendations? And what's going to happen with climate change? And as we move into the late part of the century, we're going to expect more intense hurricanes, and are we going to continue using historical information? Well, that's not the very good path to go. So there's been some global wave assessments in the group called COWCLIP, Coordinated Wave Climate Experiment. And there've been a lot of runs for global climate, but the wind fields in the global circulation models are underestimate the wind speeds. The wind speeds are underestimated, so the resulting waves from tropical cyclones are underestimated. And there's also very low resolution to resolve enclosed seas. So what we've been doing, not as we cannot use the global circulation models, is that we've been using tropical cyclones derived or synthetic tropical cyclones, which are derived based on the model using the physics of the hurricanes, where 12 meters per second vortices are randomly seeded along the ocean. And depending on the ocean conditions and the atmospheric conditions from reanalysis, these protostorms either decay and phase out, or they evolve to tropical cyclones and they intensify based on different models. So that way we can get whatever number we want of tropical cyclones in our area of interest, and we can do more robust statistics in areas with a low frequency of tropical cyclones. And we can do the same methodology, but now these events are derived or they're steered by the information from global circulation models. In this case, we use 6 different, the ones that are in the screen, to derive the tropical cyclones. So these are not the tropical cyclones from the global circulation models. The information from the GCMs are used to derive this event. So we are not underestimated the wind fields. So this is, in short, the methodology. We have the synthetic tropical cyclone database. For the present climate, we use reanalysis as a reference, and then we use 6 different global circulation models. And then we have the future climate for the 6 global circulation models under RCP 8.5. Together, we create the wind fields for the tropical cyclones using a parametric model, and then we run a 3rd generation wave model to obtain the maximum envelopes of significant wave height and other parameters. So we get maps like this one, where during the lifetime of the event, we get the maximum of those parameters. So we do that for all the synthetic events, which can be, well, we did it, they vary depending on the model, but there are around 1,000 events that were modeled. And then from those, we use extreme value analysis to establish recommendation values for design. And this is the results from the ensemble. I'm not going to show the validation or the calibration, but this is on the left is the present day wave climate based on tropical cyclones. So this is extreme wave climate that derived from tropical cyclones. And sorry, it's also the 100 years return period wave climate. And on the right, we have the RCP 8.5 scenario for the end of the century. And we see that there's a generalized increase in the significant wave height, which has profound implications in the design of structures. So I'm going to show you a comparison with the recommendations of the API. So the API provides the design values for the 3 different areas shown on the left. And on the right, there's 3 plots showing the API and the historic results on the solid black line, and then together with the results from the synthetic events. So the synthetic events related to derived from the reanalysis green, and then on blue is the present climate, and red the future climate, where the solid line is the mean of the ensemble. And we can see the uncertainty on the ensemble. So we can see that for the future climate, in all the regions, there's a generalized increase in the significant wave height independently of the return period. And what does that mean? That means if we design a structure today and we use 100 years wave for the design, as we move into the future climate, that same wave height, in this case of 14 meters, will be corresponding to a lower return period. So in this case, in the plot, we see that it corresponds to a 34-year return period, the same 100 years return period, but now for the future climate. So if we design a structure now with 100 years return period, and that structure had an estimated lifetime of 30 years, the chance of the 100 years return period wave presenting during the lifetime of that structure, it's only 26%. But if that return period goes down, then in the future climate, that same wave will increase its probability of occurring to a 64%. So that translates to probability of failure. So we have, if we're designing with the conditions today, we will have more probability of failure in our structures if we don't use a non-stationary wave climate for their design. So saying that, the conclusion of this work is that estimating waves for design using historical data is inaccurately considering the short historical record. I didn't mention that, but the historical record of tropical cyclones is only since the satellite area is only accurate. So we don't have a lot of years, and in many areas we don't even have events, and they could be events presenting in that area, but we just don't have them in the historical record. So the synthetic tropical cyclones can allow for a more robust characterization of the wave climate, including the design waves for different return periods. So as we shift to a global warming scenario, we should be using non-stationary wave climates to reduce the probability of failure of structures. And the synthetic tropical cyclones, it's a way that we can do it. Of course, I just had to say that this is very focused on structures, and probably under a climate change future, we should also be thinking of other types of solutions. But I don't see how we can do that in the offshore area. So I think we still need to use non-stationary wave climates for the design of structures. So that's my talk, and I just want to thank the people that has been collaborating with this work. So thanks very much.
Thank you, Dr. Appendini, for your very punctual, interesting insights on future scenarios on extreme meteorological, coastal, and wave events. And finally, I have the great pleasure of introducing Dr. Guillermo Murray-Tortolero from the Institute of Ecosystems and Sustainability Research, UNAM, who will provide insights on food production in Mexico and its correlations with climate change. Dr. Murray's research focuses on the impacts of climate change and extremes on a broad variety of topics, including ecological, social, and economic. He employs big data analysis to find connections between different physical, ecological, and social processes of our planet with the objective of elucidating how climate change alters these links. Welcome, Doctor, and thank you for being here. The floor is yours.
Thank you, Fernando, for the introduction. Can you all hear me without problem?
Yes. Very well.
Perfect. So a special thanks to everything for this invitation. Today I'll be talking about how drought has impacted the food production systems of Mexico, a brief outline, and how this translates in impacts for the people who directly depend on food production. So the idea comes from this tight coupling between climate, our own evolution, and crop domestication over the last 10,000 years. So this period we know as the Holocene has been remarkably stable regarding climate, and this allowed us to domesticate our crops. So pushing the climate boundaries beyond these predictable patterns is a disaster for our food production systems, and this is what's happening with climate change. But when we think about climate change, we're actually referring to three different aspects of climatic variability that we are altering. They're all happening at the same time, which is difficult sometimes dividing each one. But we are talking about changing in climate averages. So the most common one is just increasing temperature. We're talking about increased variability. So we have the same climatic average, for example, the same annual precipitation. We are seeing more extreme events. We're seeing more droughts and more flooding, for example. And the last one is that we have the same variability, we have the same average, but we're seeing a change in symmetry of the climate. For example, precipitation, instead of falling during the rainy season starting in May in Mexico, is starting in June or July. And these all have different impacts on our food producing systems. So I'm going to briefly show how this looks for Mexico and how climate has changed in the last 70 years. And then I'm going to show you the impacts of these changes. So on average, Mexico is warmer now than it was 70 years ago. We gained about 0.7 degrees temperature between 1950 and 2017. a bit more if you take into account the last 4 years. And we have not seen any change in temperature. Temperature has been remarkably stable over these 70 years on average, but we are seeing an increase in these extreme events and increased seasonality. So what we have here is just the month of the year, and then we have two lines. The black line is the 1950s, and then we have the brown line, which is the last decade of the analysis. And we have then the wet season and the dry season, and we have precipitation minus potential of transpiration. This is just a metric of total available water across the country. And what we're seeing is an increase in available water during the wet season and a decrease during the dry season. So we're getting wetter wet seasons and drier dry seasons on average across the country. And what's interesting is that the number of rainy days hasn't changed in these 70 years. So basically, we're seeing more water falling during the wet season on the same number of days, which means an increase in storms and stormy rainfall, and then a decrease in water availability during the dry season. This has important effects and important implications for the three different forms of food production in Mexico, which are irrigated crops, and then we have rain-fed crops, and we have livestock. And they're all depending on climate differently. And the last thing that we're seeing regarding climate change in Mexico is an increase in extreme events, particularly drought recurrence. So we saw a remarkably strong drought in 2011, so that was 10 years ago, and the recurrence of this drought should be every 30 years. So the last one, as extreme as this one, was during 1986. But now we saw a drought this year. So last December, this January, and this February, we have a drought as intense as the one 10 years ago. And it's very likely that we're going to have another drought this year pushed by La Niña, at least for the first 2 or 3 months of the year. So we're seeing this increment in drought intensity and recurrence as well. And all these changes, the change in average, the change in seasonality, and the changes in the recurrence of drought have strong impacts on how food is produced in Mexico and how this affects the people who directly depend on this. So the first type of change linked to trends is the expected impacts on rain-fed agriculture. So what we have here is just 4 RCPs for CNIP 5 scenarios. And we have the rain-fed maize yields, expected rain-fed maize yields. So best scenario, the 2.6. We saw a slight increment in production and yields, not different from 0. But on the most extreme events, we see a decline up to 10% in maize yields and main production, with regions declining up to 30%. So this is mainly driven by a decrease on average precipitation across the country. Maize is like an umbrella for every other rain-fed crop. So what we're seeing here is not just the expected impact on maize, but potentially the impact for all rain-fed agriculture. So this decline in expected precipitation across the country could have strong impacts on rain-fed agriculture production, which is the basis of the subsistence for small-scale peasants. Then the second type of thing that we've been seeing is this increment in drought and extreme events. So this is the event of 2011 I was talking about. So what we see here is the mean annual precipitation for the country from 2006 to 2017. And this is the 2011 event. So we saw a decline in 12% annual precipitation, which lasted up to for 12 months on average, 12 to 14 months, depending on where you were in the country. And what we have here is the cattle population for the whole country. Then we have the goat population and the sheep population. And it was growing, all fine. And then we see this strong drought, which meant we lost about 1 million heads of cattle. And these animals are not slaughtered for meat. So we don't see an increase in meat in the meat markets, not exportation, not imports. We don't see an increase in animals being slaughtered in the slaughterhouses. So it's basically animals that died on the fields because of drought. And the same things happened with goats. What's interesting with goats is that they never recover after this event. The population decline and it stayed low duration of the next years. Sheep, they don't seem to care about this event when you see the annual numbers, but there are important regional differences. So this is just the same event, but seen across the whole country at state level. So this was the precipitation anomaly. It hit 85% of the country. It hit 85% of the country, and then we have again the anomaly in the population of our livestock animals. So we see a decline, a really strong decline in Zacatecas, up to 30% decline in the livestock, the cattle population. And the same with goats. And then with sheep, sheep are mostly located over these two small states, which are Hidalgo and South Mexico, which were not as strongly affected as other states, which is why we don't see this decline in global numbers. But there are some strong local, regional decline in sheep population. So this drought event affected the whole of the livestock population in Mexico. We saw a massive decline in numbers. And of course, it altered the lives of people who directly depend on this. And this is the jump when we see how this translates, how this impacts in food producing systems translate into the livelihood of people. What I'm showing here is just the migration rate from Mexico to the United States of these 40 years, from 1970 to 2009. And in the circles, we have the average for the period, and in triangles, we have the average for dry years. So it's just the driest year in each decade, and then we just average all of this. And then we divided Mexico in two sections: rural environments, which is populations with less than 15,000 people, and then the urban environments, so cities. And then we have a division based on background climate. So we have the arid regions of Mexico, which receive less than 500 millimeters of rain per year. We have the semi-arid, which receives between 500 and 1,000 millimeters, and then the humid, which receives more than 1,000. What we see here is that for every single region, no matter how you divide the country, during the dry years, we see an increase in migration rates from Mexico to the United States. And this is quite dramatic from some of these divisions, right? So the rural dry environments see a doubling of their migration rates, and the migration rates almost 1%. So during these dry events, 1 in 100 people decided to migrate to the United States. So droughts across Mexico has strong impacts on food production, particularly rain-fed agriculture, and then it has strong effects on livestock population, which pushes people decision to migrate, right? So if you were already thinking, well, maybe I'm not doing so well, I should seek better livelihood elsewhere, then you have these events that push these decisions, and we see this increment in migration rate everywhere in the country. And extreme events have other implications, have many other impacts. The first two, I know they've been documented for Mexico. These other have been documented for other countries, and I think it could be potentially similar in Mexico. So, for example, we have the Bruchtal paper, which shows clearly that the increase in temperature we're seeing across the country is related to an increase in suicide rates. It doesn't matter if you are in a wet or dry system, or if you are in a cold or hot system. During the increase in increased suicides, and similarly, we're seeing this increase in school abandonment during droughts. So this is just proof for the northern states of Mexico. But what we're seeing is that during these drought events, families are left with less income, which then forces them to make their kids leave school, abandon school, particularly high school students. And then we have also seen these impacts of drought and extreme events on other social problems like domestic violence. So temperature has been linked to an increase in increased temperature has been linked to an increase in domestic violence, in car crashes. This is for Australia, and also in fertility problems. Potentially, there's also been a link between drought and an increase in criminality in urban areas. So this is all the frontiers in research that we're still haven't fully understood. And I think they deserve our attention, particularly to generate information for the policy relevant information. Thank you.
Thank you, Dr. Murray, and to our audience. If you have any questions, I ask our speakers today to write your emails on the chat so they're able to send you their questions. Thank you very much. And thank you for accompanying us today. Now we'll move on to our next keynote speaker from Mexico, for which I'll give the mic now to my colleague, Rodrigo Melendres from the Mexican Embassy. So the mic is yours, Rodrigo. Thank you very much.
Thank you, Fernando. Apologies for the delay on the technical issue. I am Rodrigo Melendres from the Mexican Embassy here in London. I am delighted to present our next keynote speaker, Dr. Enrico Yepez, who is a tenured professor at the Instituto Tecnológico de Sonora and has been part of the national system of researchers of our National Council for Science and Technology, level 2 since 2015. He has published over 50 manuscripts in journals of international circulation in the areas of earth and life sciences. He also has been the main researcher in projects with funding from bodies such as National Council for Science and Technology and the International Atomic Energy Agency, and is a keen participant in various collegiate network initiatives. He is currently part of the scientific steering committee of the program Programa Mexicano del Carbono, PMC, in the area of atmospheric sciences, and from where he has made efforts to promote the development of biogeosciences in Mexico. Without further ado, I'm going to give the floor to Dr. Enrico Yepez. Thank you for being with us, and thank you for accepting our invitation for this two-day conference event. Please, Dr. Yepez.
Thank you very much, Rodrigo, for the introduction. Let me see if I can share my screen. So, well, thanks for the introduction, and also thank you very much for the organizers for this event, which has been very insightful. Thanks for the authorities that presented this morning and gave us some insights of what are expecting from the science community for these important and pressing issues that we're facing right now regarding climate change and the actions that we can actually take as a scientist. So I'm going to try to just introduce briefly some of the work that we've been doing in my research group here in Mexico at the northwestern part of the country in Sonora. So most of the work that I'll be presenting comes from my students and colleagues here in the university. And well, so basically the work that it's been that I will be presenting, it comes from some of the recalls that we're doing after this huge event that we had a few weeks ago, the COP26, which was part of what inspired also this binational interaction. So there were a lot to be said in this conference, but some take-home messages that we can engage on, and particularly regarding the expertise that it's been growing in my research group, are these three important points: that there's an urgent need for the greenhouse gases reduction so we can stabilize warming. And this is important because it invokes international cooperation, which is what brings us here today. And it's always been important to invoke international cooperation for these global issues. It's very difficult, as we've seen in several climate change scenarios, to work regionally in a globalized world to deal with global problems. So we need international cooperation at all times for these issues. There is a fresh attention to manage potent greenhouse gases as nitrous dioxide and methane. and especially because it involves attention in the food sector. Agriculture and cattle grazing are huge emitters in this planet, and there's a fresh attention to this. I'm not going to talk about this today, but I think this is a very important point to keep in mind. And what is really interesting for me and is actually inspiring in these days is thinking about these natural climate solutions that we can bring by managing and taking care of our ecosystems, because it's apparently a contribution that we can make from the science perspective to tackle these climate change problems. These natural climate solutions, as you know, are these strategies to preserve or restore or improve the way that ecosystems are right now. We know that these ecosystems are connected through the biogeochemical cycles to the whole biosphere or to the whole Earth planet or Earth system. And as so, their dynamic, their function, the exchange of water and carbon and other nutrients actually have an imprint on what's happening in the planet. So attributing these effects to different ecosystems and how they're managed, it's important to use these ecosystems as solutions to mitigate these climate change issues, in particular emissions. As we can see in this figure, if we manage or we propose how to manage different ecosystems, we can perhaps propose different levels of mitigation that we can get to managing these systems. It is important. The potential for a mitigation strategy is big. However, as you can see in the figure, the uncertainty for these implementations is very big. So it's costly in some instances. In some instances, it's not too costly. But the bottom line is that it's a very, very uncertain application, and this uncertainty basically comes from the poor knowledge that we have in some instances about the function of these ecosystems. So we know how the basics of our ecosystem, we know a lot of the diversity, the conditions. We can monitor this ecosystem from space in these days, but we know very little about fine processes and mechanisms and functions that we have in this ecosystem. So if we want to use ecosystem stewardship or management as a natural climate solution, we need to learn more about the function, and to do this, we need to associate to monitor the associated emissions that come from the ecosystem functioning. So this brings us to a big challenge in a country like Mexico. We are an important country, about the 13th place as an emitter in this planet. We have a very diverse country, a mega diverse country with beta diversity. That is, diversity is just gathered in a small area. There is transitions in relative short distances. We have an area of about 2,000 square kilometers, which is a reasonable size of territory. We have a population of about 130 million people. We have an extensive coastal area, which brings a very interesting aspect to our ecosystem. We have a very complex orography. We have two sierras, in the eastern and the western sides of the country, a volcanic belt in the center part of the country, which brings, it's part of what we have this megadiversity, and it also has an effect on the climatic conditions where these ecosystems engage, because we are just outside the part of the country, just outside the subtropics. We have the occurrence of the northernmost limits of very important ecosystems like the tropical dry forest or the mangroves, which also brings an interesting setting for studying these types of ecosystem, because we can already study these ecosystems at their extremes in temperature and water limitations, perhaps. So this brings us an opportunity to engage on ecosystem science in Mexico. So one of my favorite topics or my favorite challenges in this country is to understand the seasonality. Just the talk that preceded me talk about how this seasonality is actually changing. So Mexico per se, the whole country for the most part, is very highly seasonal. We have half of the year is dry and the other half of the year is wet. So that brings a very switch points on how the ecosystem function. The energy flow and the water flow in these two times of the year is very dramatic. So we have not just a large country, but two very important phases of the country that we need to study and understand the processes associated to demand in the face of change, as we just heard. So another big challenge or opportunity is that because the population in our country is widespread, we have an important population living in the coastal areas as well as in the sierras and important urban settings. And this basically is putting pressure on the ecosystems. We now have across the whole country, it's just a mosaic of successional states. We have remnants of mature forests and mature mangroves and mature grasslands and shrublands, but we also have very disturbed sites, heavily grazed or heavily areas used for agriculture. So this is basically bringing a very dynamic setting across the country to understand how one single ecosystem, let's say the shrublands, will be functioning. So this is just to mention how the importance of monitoring these changes, how it multiplies the difficulties to study these issues in the country. And sadly, we have poor information about this activity data. So our agencies make their efforts, the academia makes their efforts, stakeholders in some instances make their efforts to document these changes, but we don't have a common repository where we can seek for this activity data to have a wider perspective on what is happening. So this is one step that needs to be clear, so we can then move to a monitoring system where function for these ecosystems can be in the center of the strategy. Besides that, we need to engage in these broad discussions with different areas of knowledge, with different stakeholders, with different participants on what is involved in ecosystems, because we know that these perturbations that we see in the ecosystem have to do with the human pressure that we're putting in them, because we need to use their ecosystem services or their natural resources. And because ecosystems are complex entities, we need to understand them in the different scales. We need to understand fine soil processes like microbial communities' performance in the biochemical cycles. And we need, as we heard today, understand what happens at the scale of a watershed, for example, to close our water budgets or to understand the large-scale dynamics of this biochemical cycle. So we need to engage on these multi-scale platforms to really gather information on the functioning of these systems. But what should we monitor? Really, this is the big question. First of all, we need to monitor what we know how to measure right with the less uncertainty possible, so we can understand how the system works. And I cannot talk about monitoring without putting this well-known graph. Just to put an example, that if Charles Keeling wouldn't have this vision of monitoring just the CO2 concentration in our atmosphere, we will not have this very important record of function in our planet. So, and besides the dramatic increase of CO2 that we're seeing, this waving increase that we see, this seasonality that we're seeing in the breadth of the biosphere is very important. So monitoring schemes like this, that not only monitoring one entity or one stock or one pool, but it's also providing information about the functioning of this system is of very high value. And as I said, we need to measure what we know and we understand. So in our group here in the Tecnológico de Sonora, we've been taking the ecohydrology as one of the flags that we have in our research. And this is because it forces us to understand how hydrological processes, how the water flowing in a semi-arid region like the one we have here in Sonora is coupled with the biological processes, with primary production, for example, how many biomass it's acquired, how much carbon is circulating in the biosphere, and how is that tied to the circulation of the water is one of the key elements that we monitor. This forces us to understand pools and fluxes. It forces us to quantify magnitudes, to understand the controls, to seek and find out what are the feedbacks and the turnover times of the elements of interest that we're seeing under this platform. So we think this this vision is of value and has given us some good expertise on how to monitor and understand our ecosystems better. So under this perspective, we have focusing a lot on understanding ecosystem fluxes. So basically, there's the exchange of CO2 between the surface, the ecosystems, and the atmosphere, which in the ecological terms we call the net ecosystem production, which is simply the net budget of carbon that is flowing between the biosphere and the atmosphere, and the evapotranspiration, which we all know this is combined flux of transpiration and evaporation that occurs when water is transferred from the surface to the atmosphere. And these both fluxes actually have component fluxes that gives us a lot of information about the mechanisms that are controlling these exchanges that are important. So like, for instance, the gross primary production, which is the photosynthesis at the ecosystem scale, is a key parameter, is the way that CO2 is entering the biosphere, one of the main pumps where we can wash out the CO2 that we have extra in the atmosphere. But because these entities are live, ecosystem respiration is an important flux that is actually returning this greenhouse gas to the atmosphere. So understanding what balances the coupling between these two fluxes is of high relevance in ecosystem sciences and in the center of these ecosystem alternatives that we need for the to engage ecosystem for as a natural climate solution. So to do this, we have relied on this technique, the Recoverance technique, which is this micrometeorological technique based on high response sensors, water and CO2, and perhaps methane and nitrous oxide, and balancing the energy that is reaching the surface and coming out from the reaching the surface from space and coming out emitted from the Earth's surface or from the ecosystems. So this technique is very useful to understand fine processes in ecosystem, because in one instance we have a very fine timing resolution. We can literally sense the pulse of the biosphere. We can measure at half an hour integration periods, and so we can close the exchange of water or CO2 in a diurnal cycle with very high precision. We can then integrate to days, to weeks, to months, and years. So we can then calculate budgets off of these techniques. We maintain these installations running for several years. We can actually investigate interannual processes in ecosystems and associate them to interannual processes or fine scale temporal situations. And the other advantage of this method is that it also integrates across space. So we can integrate by several square meters or 2 kilometers even, depending how we set up our installation and the properties that we have in the terrain that we're measuring. So this technique is very potent to understand ecosystem process and in real time at an appropriate scale, because we are integrating all the components that are contributing to the gas exchange in these ecosystems. So I'm going to show one of the examples of why the information that we gather from these monitoring schemes can be useful to understand ecosystems and then to make proposals for moving ahead at one point for a natural climate solution. So the subtropical shrublands that we have in the northern part of Mexico, just in the bottom part of the sierras, not necessarily to the coast, this yellow stain will be the one that basically marks this type of ecosystem here in Sonora. In this site, we have actually tried to model ecosystem processes. Basically, we have tried to understand how the water and the carbon is exchanged in this type of ecosystem. And the way to do this, we try to parameterize and to calibrate and use an ecohydrological model coupled to a soil carbon model, so we can predict or model one of our key fluxes, the net ecosystem production, again the net carbon exchange, after understanding the processes of primary production, the processes of respiration, not only in the vegetation but also in the soils, so we can couple the whole ecosystem as exchange, a CO2 and water exchange system. So we use this eddy covariance data, the data from our towers, to calibrate and to validate the importance or the performance of this model. And we try to we start at least thinking on how we can move to potential ecological forecastings once we have a good grasp on how this an ecosystem like this problem works. So apparently our effort to calibrate and to work with this model was valuable. Now you can see the calibration, first of all the calibration and then the validation period. Basically half and a half of the data set that you see on the screen gave us a good resolution, so we were able to parameterize appropriately our model. And with that, we were start asking questions on how this problem will respond to future climate conditions. We use a drastic scenario. We just went all the way to 8.5 in the RCPs. So we can have a very drastic manipulation. We're doing a numerical experiment basically once we had our model calibrated. And we learned two things that are very important. Once, when we basically increase the temperature as is expected in the next, let's say, 40 years, we saw, as we see in this graph, with these probability density functions, that how the net ecosystem production, the photosynthesis, deviated. So it reduced in comparison to the historic record that we had for the photosynthesis and the net ecosystem production for this system. So we had we noticed a decrease on this, an effect on this temperature on the performance of this system. However, because as we know, when we, as the climate is changing, CO2 is increasing in the atmosphere, and that's having a fertilization effect on ecosystems. And when we turn on the CO2 fertilization effect on this simulation, we notice how the conditions weren't as drastic as they happen only when the temperature was changed. So, and we, at the end, what we saw is if we just focus on the black and the reds here, basically the net ecosystem production and the water use efficiency, which is the ratio of the photosynthesis and the transpiration, we actually saw how once we put the CO2 model and the temperature effect, basically the effects of the climate change were unnoticeable. This is the average of 3 different downscaling models that we use to fit on the climate variability for our model. But if we see the average of these models for net ecosystem production, basically kept it the same. But there was an important difference on the water use efficiency. So our ecosystem, despite that didn't increase on productivity, it actually improved its water use efficiency, which can be certainly an important trait for future climate conditions. So if this were true, this is an experimental model effort, but validated through data, we can make proposition on how to use this type of fragments for natural climate solutions. Similar here in Sonora, also investigating on the tropical dry forest, which is also a very important ecosystem in this region. And actually for the Americas, you can see these black stains basically representing the distribution of this type of forest within the northernmost limit again. And as I was mentioning, this is a very fragmented landscape. We have several different successional stages. This ecosystem is very attractive to burn, slash and burn, so we can introduce cattle and graze them, put pastures, artificial pastures to graze them for some time, then abandon them, and then let the systems for their own succession and recovery. So we have really in the Sierra a mosaic of these different patches. So it's important to understand how these different landscape conditions are influencing the biochemistry and the CO2 fluxes. So that's what our group did. This is part of the dissertation work of Nidia Rojas, with these 3 installations, one in an early succession site, one in a secondary succession site, and one in an old-growth forest, running simultaneously, waiting to compare how the CO2 and the water exchange occurs in these systems. And we learned several things, basically. Despite that they're in the same climatic conditions, we were lucky to have different rainfall years, variation in our data sets. Again, with this information, what we're seeing is how in time, we have the precipitation, the cumulative precipitation, the evapotranspiration flux across the three different landscapes, and the net ecosystem exchange of CO2, which is basically how much CO2 is entering or leaving the surface. As we can see, 0 will be neutral, no entrance, no exits of CO2. If we see positive numbers here, we're seeing a net loss of CO2. And then if we see negative values here, we're seeing a net sink of CO2 to the ecosystems. And just in a glance at this just particular year, you can see how the two secondary systems, which are the red and the black, or the green and the red, are the secondary sites, are being net sinks of CO2 later in the growing season when the rain is active. But we're seeing some more erratic fluctuation on the net ecosystem exchange for the old growth forest. Because NIDIA and the group have been able to maintain this installation through time. We've been able to assess now for 5, where we're going for the 6th year, assessing these exchanges of water and CO2 in the system. We've seen these differences. We can see how, in relation to precipitation, the ET, of course, tracks precipitation very nicely across all sites. But the net ecosystem exchange changes. So the secondary forest, which is a very actively growing forest, gains more carbon, has a net sink of CO2 for most of the time. Then the yearly succession, which is a recently abandoned site, is gaining carbon, but not as an extreme as the secondary site. But when we look at our growth forest, we're seeing that it's a net source of CO2 to the atmosphere. This you can see the blue line here is showing values that are actually leaving the ecosystem. So at the end, across the whole year, we're seeing a net loss of CO2, which is a surprising result because we were expecting that a well-preserved ecosystem, an all-growth forest, will be a more strong sink of CO2, but because apparently this accumulation of biomass that we have through time, as this forest grew and it was not disturbed, it ended up storing enough biomass to end up as a net source of CO2. So how would we be representing this type of variation in ecological modeling or larger scale models, as we saw earlier today, to understand better these systems and to propose them as a natural climate solution? This is intriguing. It's still very complex. So, but we need to know this before we can move to the next step. So, and another nice and final example that I can talk about is in our semi-arid mangroves here in the Gulf of California, which is also reaches the northernmost limit here in Sonora. If we compare two structurally very similar mangroves, one in the northern part of the state in a very well preserved area, in the Estero El Sargento, in the northern part of Sonora, very close to where Isla Tiburon is, like in the beautiful Sonoran desert. And then we compare with a mangrove that is right by the edge of the Yaqui Valley here in southern Sonora, just a few kilometers from where I am right now, under the influence of all the drainage, agricultural drainage that occurs from the Yaqui Valley. So you see, same structural ecosystem, but with very different background on or setting, spatial setting on an anthropogenic pressure that they have. So basically what we see in this ecosystem is that the net ecosystem exchange across one whole year, this is a master's thesis also done in the lab by Marta Vargas, we basically notice how the two ecosystems are actually net sinks of CO2 in this case. We can see this, the fluctuation in real time across times. And if you pay attention to this period, which is in the summer when temperatures change, there are fluctuation responses to temperatures. But if you see this part of the year, when this ecosystem in particular, the Tobari Bay, the one that is close to the Yaqui Valley, is being influenced by the agricultural drainage. So this is the period where the wheat season occurs, basically. We can see that the net ecosystem exchange is fluctuating close to zero, and in some instances it's actually been a net source of CO2 to the atmosphere. We don't have enough information to make an assurance, but we believe that this occurs because these drainages that occur from the Yaqui Valley, exacerbate the respiration on the phytoplankton, and actually on the actual mangroves, these nutrient loads exacerbate respiration, which turn the net exchange of CO2 not as a net source, but if you see it, compare the net gains is 2/3 less on the anthropogenic influence site is 2/3 less CO2 gain than the one that has on the pristine mangrove. So this gives us another perspective of how these anthropogenic pressures and the capacity of response that the ecosystems have to, in terms of gas exchange and regulate the CO2, in this case in the atmosphere, can have different influences. It will be really interesting to see how methane, for example, responds to these different managements. There will probably certainly be important difference and will be important to study in further efforts for monitoring. And well, with these examples, I hope I can create a perspective. We can keep giving examples across country. So if we work together in the different sites that are instrumented, different ecosystems that are instrumented in Mexico, we can start investigating these differences. This is one of the things that we've been starting doing, working with the Programa Mexicano del Carbono, which is this academic entity that is forming as an academic muscle to engage on the dialogues and discourses about climate change and the potential of ecosystems to mitigate these changing forces. So we created a first report where we started synthesizing the information not only from the flux community, but also from the forestry community, from the soils community, from the wetlands community, and etc. So it's an important document that reflects some of the state-of-the-art in research that we have in Mexico regarding the carbon cycle. In the flux community, with some of the synthesis that we did in this first effort, we can see basically quickly that our ecosystems are very variable. This is the net ecosystem exchange of CO2. So we can see how our forest plantations, temperate forest plantations that we have in the center part of the country are huge sinks of CO2 from the atmosphere to the ecosystem, and it's a managed plantation. So we can see or think about very good potential to manage our forest plantations to sink carbon from the atmosphere. Of course, our blue carbon, our wetlands and mangroves are also very potent sinks of CO2, as we just saw. Even with an anthropogenic perturbation, we can actually see net gains of CO2 from the atmosphere. Is something very important to study, to understand with a finer detail on what is the actual potential of our blue carbon in this country to contribute to these mitigation strategies or natural climate solutions. So we can keep talking about examples in the country, but at the end, what will be important is to insert on a wider scheme what the effort of Mexico is doing in this regard. Basically, if we were to try to understand the net ecosystem production across the globe, we can do it. And well, people is being
Professor Yepez, you have 2 minutes to conclude, please.
Okay, Tim, I'm pretty close to finish. Thank you. So if we can validate these large-scale models, we can reduce uncertainty. We can see we have assessments, but we have important uncertainty that we have to deal with. Creating or having empirical data that is actually contributing on specific climatic regions can perhaps contribute to reduce these uncertainties. And finally, we can, people, the flux community is starting to debate on how we can really move from these monitoring schemes, from this, if you want, very basic scientific information to an actual application. We can start seeing that because in forests, blue carbon and grasslands, our observations in Mexico fit a very important climatic region. We can contribute, and we are understanding about the fine controls on carbon pool changes. We saw this dramatic example with the TDF being a net source to the ecosystem, or the susceptibility of mangroves to anthropogenic influences. We can relate. It's very easy to relate biophysical feedbacks. We're talking about extreme events. Is if we have a long-term data set on the functioning of an ecosystem, and we have an extreme event occurring in our observations periods, we can assess and calibrate models. As I heard, is a very difficult aspect to do when intermittent conditions occur. And if we maintain this our installations. No, we can assess interannual availability. And by the way, with the Recoverance technique, we can measure not only CO2 but other entities that exchanges between the surface and the atmosphere, and we can certainly assess the potential for greenhouse gas emissions in other contexts. And with that, I'm just going to say thank you. I'm going to leave with this reflection. We want to get to the natural climate solutions, but we're still very far from there. We are having serious troubles on maintaining our monitoring systems for fluxes and for function in our ecosystems, basically for a lack of interoperability between our academia, our government institutions, our stakeholders. We need to create a more stronger governance systems to understand and clearly transmit these messages that we are certainly all understanding, but we need to interoperate them so we can move forward to more countrywide and really engage in these bilateral or across the globe actions to use our ecosystems as a natural climate solutions. And with that, thank you very much.
Thank you. Thank you very much, Professor Yepez. You have presented us a very interesting and thought-provoking presentation. And of course, one that shows and is testament of the first-class, top-notch research that is being conducted across our vast network of public research centers in Mexico. And obviously, one that opens a great an ample room of opportunity to engage in collaborations with counterparts, academic counterparts here in the UK. While we wait to see if there are questions from our audience, I would like to take the opportunity to ask one of my own. And I'd like to go back a bit to the first part of your presentation when you were referring to natural climate solutions and how the cost of implementing them is a deterrent to bring them forward. To put it differently, what would be the right incentives for academia, government, and civil society to actually come together and be able to implement them, to enact them? What would be your suggestions on that?
Well, Rodrigo, this is a huge question. You let me out of breath. I guess that's the question. I mean, I'm not sure I have an answer. We have a long way to go, because we do have the institutions, the capacities, the expertises. We love our ecosystems. Mexico has an enormous history of natural history, of exploration of our ecosystem. We know a lot about our natural history. We're starting to learn more about the functioning, but it's complicated because you need to monitor across time, and that is costly. Our institutions usually circulate in 3 years or 6 years. So our research programs are sometimes 1 year, 3 years, and 5 years. And that's not enough to actually establish a long-term monitoring program. We need a more institutional support to actually have an established and government-supported platforms where we can monitor with interoperability, with the standardization, which is also important, so we can have this baseline data to then experts from other fields can rely on these baseline observations, so we can then make inferences or put it on the appropriate knowledge, fields of knowledge for what we want to use these applications. So that's expensive, and requires engagement of the institutions, the academia, the government, stakeholders, and everybody. So it's a hard question. It's just I'm not sure how we all have to wake up and really make the connection. And one point, these exercises, IMTA, I know, is very sensitive to these things. I've discussed this with Agustin several times, and we know that we need to do it. We try to do it as much as we can, but there are some barriers still that are not letting us be so fluent on these engagements sometimes.
Well, hopefully, as you said, this type of exercises will help in going towards that direction through international cooperation or establishing networks beyond our own national context. So thank you very much for your excellent presentation. So far, we have had a very interesting and intense program, and I want to encourage. Well, actually, I want to first thank our audience and all our speakers so far for joining this initiative. Thank you very much, Professor Yepez. We are going to have a short 20-minute break, after which we will go straight to the post-grad research segment of our program. I really would like to encourage to stay with us after this 20-minute break. This is also an important part of our agenda, and one that will be fundamental in understanding from the perspective of young academics or aspiring researchers or people with a fresh view on the topics and issues that we have been discussing throughout this day. So thank you everyone for joining us so far. I invite you to stay with us after this 20-minute break. We will be joining at 6:30. And please, if you have any questions for Dr. Yepez or any other of our speakers today, drop us a line using the chat box, or if you're using, if you are watching our streaming through social media, leave a message in the comment box there. Thank you so much, and we'll see you in a few minutes. Thank you.